what period trend is. Questions on that? Okay, I'm going to let you guys investigate a little bit today. I mean, we've got a little bit shorter day today. So, I mean, it's not like we can't do it. So, everybody guys understand this equation and how it works? What happens to force if these plus and minuses become bigger? What happens to the force? It gets bigger, and it's directly related. If this charge doubles, then the force doubles. Because distance will say, we'll assume the distance stays the same. Don't look at the half because that's not part of the equation. Okay, but that would be your setup. Now, if distance gets, yes?
What unit do we use for distance?
Meters. Now, you're not going to plug any numbers into this equation.
Okay.
All you're going to do is show that distance, if distance decreases, then the force increases because it's inverse. Does that make sense? So that's all you're doing. You're just using the equation as a way, it's better than plugging in numbers because you can go, hey, the charges increases on this one level and the charges in the nucleus increases, and so that's why you have greater force. Makes sense. Or you can say, well, since the distance gets shorter between the nucleus and the electrons, there's a greater attraction for that electron by that nucleus because the distance has now got less. Does that make sense? Okay? So that's really all you're doing. It's a really, really good tool to use in which to explain concepts about forces of attraction. So, and that's all you would do with that. Questions you got on that? So, I'm glad we went through that. That's something that we're going to use quite a bit. And then this is just the written part of this. So this is just saying this equation, we're going to write it out. And it says the magnitude or the force of the attraction or repulsion between 2 points. These are your 2 points, like two electron and a proton, like a cation and anion charged atoms, are directly proportional to their charges, meaning if they get bigger, force gets bigger, and inversely proportional to the distance squared, because as the distance increases, then force would decrease, and vice versa. If it gets smaller, then force would get bigger. So that's an inverse relationship. You might have a little bit something different than this. I rewrote that, but I mean, yours says distance squared, I think. So it's the same idea. Okay? We're going to look at main group elements. This is the reason why. So if I explain this to you, or like if I was one of you and I had to explain this concept to somebody else that didn't know what was going on, then I'd say, hey, look at group 1. Look how the radii in angstroms increased as I went down the group. And this is why I think the reason is for that. Because as you go down a group, you add on extra energy levels. And extra energy levels means they're farther from the nucleus. And when they get farther from the nucleus, it makes the atom bigger. So then that would be my argument. And I would be okay with that argument. And I might have another list of elements going down. Okay, make sense? All right. So let's look at the other argument. So atomic radii, I give the notes for that. And then we have a period trend. So you guys look across a period and tell me what you think the trend is for atomic radii. You guys tell me what you think the trend is for atomic radii. So just go across group 1, 2, 13 through 18, and see if you see a pattern that occurs. Okay? So I would not take the first period, hydrogen and helium. You could. There's only 2 elements in that period. But you would definitely look at period 2, 3, 4, 5, 6, and go across those. So what are your thoughts on the period trend for atomic radii? Yes?
It gets smaller and farther to the right.
So it decreases in size as you go from the group 1 to group 18. Do you guys see that trend? Is there any in there that you say, wait a second, it doesn't do it here. It doesn't hold true here. Is there any of those examples? You see any? I haven't looked at it. I mean, I can look at all of them, but you guys are. Is there any that don't hold to that trend? They're all that way? Well, that's good. I mean, anytime you got something solid and that's solid, where every place you go to the right, it is getting smaller. So the trend is, if you guys want to add this to your notes, the trend is to decrease in size as you go from left to right on the periodic table, or from group 1 to group 18. Okay? Not including the Ds. We're not looking at the Ds. So the atomic radii decreases okay? All right, so some of you guys are juniors, and some of you will be taking the ACT test. And a lot of things driven data on ACT tests. ACT tests, some of you guys are going to take this year as sophomores. Probably in the spring or the summer, you're going to start taking it. And the ACT test is a test that kind of, that you would send into a college to get accepted into that school, to be able to go to that school. Some schools have a minimum ACT that they require for you to have, to go to that school. In athletics, there's a certain minimum ACT score you have to have, or you can't compete in division, like Division I. They have certain things. But anyway, it's important for you. It's one of those things that colleges use to see if you'll be accepted into the school. You can get scholarship money, of course, for that as well. Okay? And a lot of the science is data-driven. So like what we're doing right now, it's data-driven. Data-driven. We're looking at a chart. We're looking at values. We're seeing trends, if they happen or not. So what do you guys think? Why does it get smaller? So I'll start with lithium. So lithium's here. Okay? That's the first one. And we'll just draw. Lithium has 2 circles. Okay, then we go to beryllium, and maybe we'll make that a little bit smaller, just a little bit smaller. That looks about the same, but it's a little bit smaller, I think. And then we'll go to boron, then we'll make that one a little bit smaller. Okay, and then we keep on going, and then we get to the end, and we're at neon. And it's that size, let's say. I'm just doing it as the red. So you see how it kind of gets smaller? So, why? Why does it get smaller? Yeah?
Because the charges increase, so the force of attraction.
Okay, so if I was doing lithium has 3 protons, and it has 1 electron in the outer shell. And then, because that's what's being pulled in, okay? So then this has got 4 protons, and it's got 2 electrons. And I'm only showing electrons in the outer shell. It actually has 4 electrons, but I'm just showing the outer shell. And we keep going. This has 5 protons, and this has 3 electrons. And then this one has, the very end, I think it has 10 protons, and it has 8 electrons. Okay, what could you use to defend your argument? That's saying that the bigger the charge, because as we go down a group, like for example, we go from lithium, and then we go down to sodium, you get more electrons. You go, lithium has 3 and sodium has 11 electrons and protons. Why does it get bigger, but as you go across, it gets smaller? So what could you do, or what could you say to prove your point? That as we go across, charges are increasing in the nucleus and in the outer shell as well. What could you do to prove your point? So I go back to this law here. Okay? Could you use that? You could, couldn't you? What's happening to Q1 and Q2? They're increasing. The electrons are increasing in the same level, same distance. Okay? And so because they're increasing, the force is increased. Can you see why distance is going to get less and less and less? Because the force of pull becomes less, or more and more and more and more. And so the distance will become less between those electrons and the nucleus. Does that make sense? So that's what you would say is your reasoning. Okay? So that would be very logical. You're using the Coulomb's law to show that, to explain it. Okay? And so here in a second, I'm going to give you guys some terms to kind of end things up. But we want to kind of look at period trend, and this is the reason. So I didn't have enough room on that. The reason is because the electrical charge on the outer level, on the same outer level, increases across the period as well as the nuclear charge. Creating a greater force between the nucleus and electrons. Okay, so the electrical charge on the same level increases across a period of elements as well as the nuclear charge, creating a greater force between the nucleus and electrons, and that's what causes it to pull in. Okay, so those are the type of things that you're going to have to explain and use, and this would be an example for a period trend. All right, so there are 3 definitions I need to give you and to explain a little bit. Because tomorrow, you guys will have, and if I have time, I'll show you the spreadsheet that you're going to be using. And now, spreadsheets can be manipulated. So when I have you have access to the spreadsheet, I'm going to have you make a copy of it. You're going to copy my spreadsheet so that you can manipulate it yourself. So each of you can make a copy of my data and my spreadsheet, and then you can just manipulate it, mess around with it, and I'll show you how to do that. Okay? This is logical. It makes sense. We know about charges. You increase the charge on the level. With increasing the charge of the nucleus, is called a nuclear charge. Then it creates a greater force, and it's going to pull that level in. And it does it all the way across for all of the elements. Okay? If you look at the D's, it doesn't really show it in the D's, because you're not adding electrons to the outer level when you do the D's. So that's why we don't look at the D's, because we're not adding electrons to the outer level there. Okay? So these are the 3 definitions you guys need to have some information about, because these are the ones that you're going to look at to see if you have some trends. So I need to give you this. It's just information. It's just definitions, and that's all it would be. Okay? So we're going to start with ionization energy. Okay, so here's what happens. These atoms will lose and gain electrons. And they'll lose and gain electrons because they want to become more stable. So some atoms, like sodium, is very, very reactive. It's very, very unstable. And so it's going to do anything it can to get rid of its electrons. And so it's going to find a source to get rid of them. Okay? You got other elements that don't want to get rid of their electrons, and they want to keep their electrons. So they'll want to gain electrons. So we have this thing called ionization energy. And it's basically amount of energy you need to put into a particular atom to pull an electron away. We have different levels of ionization energy. The measurement is in kilojoules per mole. So basically it says if you got a mole of atoms, to pull out a mole of electrons, you have a certain amount of kilojoules. We know joules and kilojoules is energy. So the first ionization energy is the energy needed to take out the first electron. So I'm coming along and for example, I'll use this as an analogy, okay? So Reagan has an electron, okay? You got an electron, right? Let's give you that, okay? He's got 2 electrons, okay? So quit writing there for a second. So I come along, and let's say that it's beryllium. Beryllium's got 2 electrons in its outer shell. Reagan has one of them. Go ahead and hold it. I'm going to take and pull that away. Okay, kind of hold it fairly tight. Fairly tight. Okay, I pull it away. All right? So that's energy I need to put in. So he has 2 electrons. Hold both electrons in your hand. Same hand. Hold them. Okay? Hold the second one tighter than the first one. Just hold it. Okay? So I reach in there. Pull out the first one. The second one, close it up tighter. Okay, not so tight. I pull out the second one. Okay, what do you think the third one's going to be like? Yeah, it's going to get even tougher to pull out the third one because what happens, do you think, what happens as you pull out electrons, then there's something going to happen. I'll let you guys figure it out, okay, because I think you can. All right? I mean, I think you can figure it out, but you'd have to really think about what happens. So the first ionization energy is going to be the smaller one, and then if you have to take another electron out, it's going to be tougher. You'll find that in your data. Okay, does that make sense? Now, there are some times where there's a huge jump. It's like, I mean, it's huge. That was a good example. I probably should have used that. The first one, the first one I took out would be really easy. But then sometimes there's a huge jump. I mean, it's like 10 times the amount of energy I need to take out the second one. So he'd be really like that. He'd be like this. And I'd be trying to get it, and I couldn't get it. And that would be the second. Make sense? They don't want, sometimes they're willing to give them up. That would be a low. And sometimes they're very difficult to give up, and that's a huge amount of energy. Meaning that you're probably not going to get that next electron out. And it's different for every group. And on the periodic tables. Make sense? Okay. All right. This next one. It's the opposite. It says, this is the amount of energy given off when an atom accepts an electron. So now we're not taking an electron out. Okay? So go ahead and hold on. Wait a second. So he has, like say, he has an electron. So what I'm going to do is when I put one in, he's going to kind of push back a little bit. Push back on him. Okay, so I put one in, push back. Okay, it gives me push back. Okay, give one and you're happy. Give me a fist bump or whatever. Okay? And I might put in another one and then, maybe one atom's really excited about getting the electron and they go crazy. And they give off a lot of energy. Kind of like you guys at Christmas time. Like, do you guys ever watch Christmas Story? What happened when he got the bunny outfit? Was he excited? Didn't have a whole lot of energy, did he? Wasn't it bunny outfit or?
Yeah, it was.
Yeah. And then, but when did he get really excited?
Red Ryder BB.
Red Ryder BB gun. He said he couldn't have it because he'd shoot his eye out. Okay? So that's when an atom is really excited when he gets a gift. I mean, an electron that really wants, it's going to give off a lot of energy. If it doesn't really get it too excited about the electron, then that's called the low electron affinity. What you need to keep in mind, this negative number, a higher negative number, the more energy given off. You think energy exiting is negative. So the higher the negative number, the more energy given off. What if it's 0? What if an atom is 0? What's that tell you about the particular atom? Yep.
It's got just the right amount of electrons.
Yeah, and it does not want an electron. If it's 0, I do not want an electron, I don't need an electron, I'm perfectly happy, leave me alone. Okay, if it gives off a high negative number, it says, I really need an electron. Okay? Really, really bad. And I'll be a lot happier once I get it. Okay, and then the last one, I'll turn it back, because I'll put it back. So the next one is, all right, let's say they're already bonded together. So you got two atoms, and they form a covalent bond, and they're sharing electrons. So now this is a little different. One is taking an electron away. Second one is adding an electron just to the atom. The third one, electronegativity, tells you something about the attractive force between the atom for an electron that's shared. Okay, we're sharing. Hey, do you guys share anything? Any type of a gift or any type of thing that you have to share? How many here share a vehicle? You guys, you share a vehicle? Okay, do you have an equal share? You don't have equal share? Are you under 50% or over 50% on your share? Under. Okay? So, the vehicle that you share, you probably are not going to have it as much as the person that has more of a share of it. Does that make sense? So, electronegativity, it's high if it's got a big share. It's going to be, it's like, it's got, basically it's got it, 90% of the time. Where 10% of the time the other element has it. So electronegativity tells you how things are shared. Now, so when you go across a period and down a group, you'll see different share levels. You'll see ones that have a big share level, which means they have a high percentage of the time. And then you'll see some that don't have much of a share level at all. They have a really low value. So that's the best I can do for an analogy for that. So tomorrow when you guys come in, what you'll do is you'll have the spreadsheet, and I'll show you the spreadsheet. Do you guys need me to go back to that previous one? You okay? Okay, you guys can put your notes away. I'll show you this spreadsheet to show you kind of what you're looking at. Probably have you in your groups tomorrow, but individually you guys can look at this on your own. You don't need to have partners to look at it, and then you guys can get together to figure things out of what kind of trend you want to tackle. You're going to have to do a period trend or a group trend of one of those three: ionization energy, electronegativity, and electron affinity. We might throw one more in. We had one more we did last year. I don't know if I'm going to do that this year or not. So I can simplify things a little bit. Okay, we'll go to this class. Maybe I have it in here. But I will put it in there later. So I'm going to have to just Google Classroom. Spreadsheet. Recent. Okay. So this looks daunting. You look at these numbers, it's like, it's just a bunch of numbers, it looks daunting. But what I have them listed here, I have them listed by the group. So this first 1, 3, 11, 9, 37, 55, 87, they're all in one group. So this whole section here is one group. Okay? So what does that group mean? Up above, I will have indications up here what all these numbers mean. This means atomic weight. This is density. As we go on and go over, they represent different values. I don't have the headings up there. For some reason, the headings aren't there. They might be down below. But anyway, you're going to just take and manipulate these. Oh, here, the headings are down here. And I'll get it fixed where those headings don't move on you, that they stay at the top when you scroll down on that. So that's kind of what we're going to use tomorrow. And you're just going to work that as a group and kind of look at these numbers to see if there's any trends. You guys see any trends right now with group 1? See any trends here? Anything goes up? This one goes up. That one goes down, then goes up again, right? So this one kind of goes up. I think this is density. I think, I'm not sure what this level is, but anyway, you can see some of them going up, some of them going down. So this goes 14, it goes to 450, 370, 336, 312, 3. That one goes down all the way, except for the first one, hydrogen. So that would be an exception to that. You know, these are all going down, aren't they? Except for the first one. Hydrogen, 1560, 1156, 2. So I don't know what that value is, but when I have the heading, you can see that. Kind of see how that works? So then you can go period trend too. All you have to do is do this for period trend. Is go here, and I'm going to sort A to Z. So now there's my first period, 1 and 2. Second period is 3 through 10. 11 through 18 is the next period. So you can adjust your atomic number to get you your trends on that. Okay? All right, we'll do that starting tomorrow, and then we may have a lab, just kind of break things up on Friday, dealing with reactivity and period trends for reactivity. Okay.